First of all, let's look at how time-driven plot and axis formatting can be done in Scilab. Here are a list of useful syntax and their functions. Please pause the video to read them. We have an example of Scilab code that can be used to plot a continuous ECG signal and a discrete ECG signal. This is the result of the code that we have used, and as you can see, it's complete with the labeling and titling. And we have what we wanted, which is the continuous ECG signal and also the discrete ECG signal.
Assalamualaikum, I'm Faizullah and I'm going to continue about the functions of the rest of the categories in phase 1. So the first category is functions for FIR and IIR signals filtering. So the function we call for IIR is IIR, and the input arguments are N, FRQ, F type, F design, delta, output arguments HZ, and for FIR the function is WFIR, input arguments F order, C FREQ, F type, W type, FPAR, output argument WFT, WFM, and FR. The second category is Z-plane plot, and the functions are, the function for FIR filter and IR filter both is PLZR, input argument SL, and output argument plot 0 pole 0 plot. And for 0 pole gain to transfer function, the syntax is the function is ZP to TF, and for filter coefficient to 0 pole gain, TF to ZP. For the last category is frequency domain plot, and the functions are FRMAG, input argument SYS and NPTS, output argument XM and FR, FFT, input argument X noise and output argument F2, ABS, function ABS, input argument F2 and output argument Y2, and WFR is the last function, which is the same as I just mentioned earlier. Thank you.
Next, let me explain how to design an IIR filter. First of all, we load the ECG signal given by Professor Sheikh Abdul Rahman. Next, we determine the size of the impulse response. In the next line, we define the range of the time, which is from 0 to maximum size of impulse response. We also define the title of the graph, the title of the x-axis, and the title of the y-axis, and plot the corrupted signal. The graph of the corrupted signal is shown at the top right. Next, we use plot 2D3 to convert the ECG signal to sample signal format, where the graphs are plotted using vertical bars. The graph of the plot 2D3 is shown at the top right. Then we also plot the magnitude spectrum of the corrupted ECG signal so that we can determine the characteristic of the IR filter we need to design. And then the graph is shown at the top right. From the magnitude response of the corrupted ECG signal, we can notice that there is a noise around at 500. So next, we define the values for the sampling frequency, low cutoff frequency, and the high cutoff frequency. And then we find the Z transform of the IIR filter to get the Hz in Z domain. Next, we inverse the IIR filter to find its impulse response in the time domain. After that, we also plot the graph of the impulse response, which is Hn. Next, we convolute the impulse response Hn with corrupted signal, which is Sn, to get the filter ECG signal. As we can see, the filter ECG signal has less noise if compared to the previous corrupted signal. And then we also plot the magnitude response of the filter ECG signal. As you can see, the spike around at 500 just now is removed. After that, we undergo Z transform for the filter ECG signal so that we can plot the Z plane with its zeros and poles. Last but not least, we plot the magnitude spectrum and the phase spectrum of the IR filter to better understanding or to see its characteristic. That's all from our group. Thank you.